the journal Orbita Mathematica, which is a new journal of UMALCA, the Mathematical Union of Latin America. So this is a generalist journal that aims at being a very selective journal, but it's just starting right now. And we are running this series of seminars in a way to promote the papers that have appeared in the journal. So Julio published a paper in Orbita, and I now giving the talk. Julio is a professor at University Torcuato di Tella in Buenos Aires. Earlier on, he also had positions at University of Buenos Aires, also in Madrid, Chile, and Alicante. I checked on MassSciNet today. He has 295 papers and many citations. Don't remember how many. So well, we are very happy to have him here. So now you go, Julio.
Great, thank you very much. Thank you for the introduction. Of course, I also want to thank the organizers of this seminar for the invitation and giving me the opportunity to talk today and present my results. Okay, the results are not only mine. My co-authors are Irene Gonzalvez and Jorge Ruiz-Cases from Madrid, and also Alfredo Miranda from Buenos Aires, Argentina. Okay, we'll talk about the minimal curvature flow, so a geometric flow of a surface with an obstacle inside, and what is the relation of this minimal curvature flow with the convex hull of the set, of the obstacle, in fact. So this talk will be sort of informal, and I decided to talk for a general audience, thinking about people that are not completely familiar with partial differential equations or with geometry. So let me start recalling something about the mean curvature flow. The mean curvature flow is a geometric flow that was very well known in the literature and very well studied. And the idea is like this: you have a surface, and you move each point of the surface in the direction of the normal vector to the surface at every point, and with a speed that is proportional to the mean curvature of the surface at that point. So if the surface is more curved, you move faster. If the surface is almost flat or flat, if the surface is flat, you don't move. If the surface is almost flat, you move very slowly in the normal direction. Okay, and you want to compute or to see what is the evolution of an initial surface according to this movement. If you start with a ball, for example, a perfectly rounded surface, every point of the ball, the mean curvature is exactly the same. So you move every point inside the ball with the same speed. So you will continue being a ball, and this ball will shrink and disappear in finite time. And it is known that the same happens for every possible convex surface. So if you start with a surface that is the boundary of a convex body in R3, for example, and you start with this geometric movement, you start shrinking, and the surface eventually will collapse only to a point. And the shape, the asymptotic shape of your surface is going to be nearly spherical. So at the end, when the surface becomes very close to the point where it is collapsing, it's going to be like a very small sphere with a very large curvature, of course. And the reason for the finite time collapsing is that the curvature increases as the surface shrinks. So that is the main curvature flow. Okay. For studying this mean curvature flow, there is an approach made popular by Evans and Sprague. And at this point, I have to say that I will not mention every possible reference. So my apologies for any possible omission, or for all the possible omissions that I will make during the talk. So this approach is based on level sets. So take a function, they take a function u of xt, defined for x in Rn, t positive, and you take omega t, the positivity set of the function, that is the interior, what is inside the surface. The boundary, the surface that you want to study is the boundary of the positivity set. Assume for this talk that everything is going to be regular and smooth. So the boundary is exactly the zero level set of your function u. So this is your surface, and you want to compute the movement of the surface of the zero level set of this function according to mean curvature, and see what is the equation that appears in u. as a function of x and t. Okay, first, what is the normal? The normal vector to a zero level set is the gradient over the modulus of the gradient, the absolute value of the gradient, because this is what we learn in calculus 2, right? The gradient is orthogonal to the level sets of a function. And what is the curvature? If you compute the curvature is the divergence of the gradient. So it is the trace of the second fundamental form of the surface, but it's the divergence of the gradient. And the divergence of the normal vector is the divergence of the gradient over the norm of the gradient. And this measures in some way how fast or how is changing the normal vector on the surface. If the surface is completely flat, the normal vector does not change from one point to another. If the surface is strongly curved, then the normal vector changes a lot from one point to the other. So the divergence of the normal vector gives you some idea of how curved the surface is. Okay, now you trace a point and you say, okay, I want to trace the points at which u of xt is equal to 0. So you take u of x of t equals to 0, and you trace this point, moving this point according to the normal velocity given by the curvature times the normal vector. If you do that, and you differentiate this equation, you obtain that the time derivative of u, you differentiate with respect to t, plus when you differentiate with respect to x and you use the chain rule, you take the gradient of u times x prime. X prime was minus the curvature times the normal. The normal is the gradient over the norm of the gradient. So this product gives you this one, and the curvature was the divergence of the normal vector. Now you expand the derivatives, expand the divergence, and you obtain the divergence of the gradient gives you the Laplacian of u, and you obtain another term that comes from the derivatives of this part of the divergence, and you get this one with a minus, with this sinus minus. So the equation says that the time derivative of u equals the Laplacian of u minus one of the second derivatives. And this one is the second derivative in the normal direction. So what you're looking at on your surface is a combination of the second derivatives, the Laplacian in fact, but only in the tangential directions, because you are subtracting the second derivative in the normal direction to your surface. So this is what you get at the end. You get the time derivative of u equals a sum of second derivative in directions that are orthogonal to the gradient of u of xt. So only tangential to the surface u of xt equals to 0. And this equation, this time derivative of u of xt, is a PDE, it's a partial differential equation that encodes the movement by mean curvature of your surface if you understand your surface as the zero level set of your function u of x and t. Okay, for all these computations and the previous one even, you have to be extremely careful because you are assuming regularity of u, and moreover, you are assuming at some point that the gradient of u does not vanish. So when the gradient of u vanishes, you run into a lot of troubles because you have to give some sense to this kind of terms of the divergence of the gradient over the norm of the gradient. When the gradient vanishes, this is not well defined. You have to make sense of all this. I am not going to be precise in what sense this has to be interpreted, but for experts or for people who knows about PDEs, all these things could be justified and has to be interpreted in the viscosity sense. So this is the mean curvature equation as was proposed by Evans and Sprague and was studied by many people. Among them, I will mention these three references. And of course, there are many other people that studied this equation, this evolution equation of a surface according to this partial differential equation. Sorry again for any possible omission. The only point that I'm going to make is that this paper by Kohn and Sarfati makes a connection with this for this equation, for this mean curvature equation, with game theory. And we are going to go back to this connection later on.
Sorry,
Yeah,
Julio.
please ask.
In the previous slide,
Sure.
the N, the big N, in the
Yeah.
summation at the end. So what does this have to do with? I mean,
It's
you
in
have
Rn. Everything is embedded in Rn.
in Rn. So
In the Euclidean space, the N, capital N, is the number of variables.
Okay, so but your surface is dimension 2.
No,
right?
it's a hypersurface in Rn.
Okay,
It's dimension 2 in R3. And
okay.
when I will make this with my hands, is dimension 2 in R3.
Okay.
Okay.
Okay. Thank you.
So it's a hypersurface. Thank you for the comment. And please don't hesitate to interrupt me at any time and make comments, ask questions, or whatever you want. This is a hypersurface of dimension n-1 embedded in Rn in the Euclidean space. And if you want to think about something, and this is enough for the talk, think about a surface of dimension 2 in R3. And this will be the model example for everything. And the difficulties are already there. So this is capital N. Yeah, sorry about that. The normal vector is not capital N, it's this nu that appears somewhere. Okay, that was the movement by mean curvature of a surface or a hypersurface in Rn. And that is the equation that appears when you look at this movement using level sets. Okay, now let us go to our problem, to our setting. First, I want to say something about convexity. What is a convex set in Rn? A convex set in Rn is the following. A set is going to be called convex if for any 2 points in the set, the segment that goes from x to y or that joins x with y is included in the set C. For example, a ball is convex, a square is convex, and many other sets are convex, but something like is like an 8 is not convex. And what the convex hull of some set, so now you are given a set K that is not necessarily convex, or the model case that we are thinking all the time, the set K is the union of 2 disjoint balls. If you take the union of 2 disjoint balls, you ask yourself for the smaller convex set that contains the 2 balls, and this is given by the intersection of all possible convex sets that contains the set K, the prescribed set K, and this is called the convex hull of your set K. So this is the minimal possible convex set that contains your prescribed K, and if K is given by the union of 2 balls, then what you get is the union of these 2 balls and a tube that connects the 2 balls. So this is the convex hull of a set. And our main goal in this talk is to find this convex hull of the set using some geometric flow. And what we aim to do is the following. You take your set K, you assume that your set K is inside a surface that surrounds your set K, and you want now to move the surface to let the surface evolve in such a way that in the limit as t goes to infinity, you obtain exactly the convex hull of the set. This is what you want to find and to show. So you want to find some geometric movement according to curvature, and you know from the title what is the answer. The answer is the movement by minimal curvature. And okay, if you move your surface according to the minimal curvature of your function, of your surface, then you will get in the limit the convex hull of the set. This is what we want to do. Okay, let us start with this thing using the same strategy as before. You take a function u of xt. You consider an initial surface S that is the boundary of a body omega 0, of a domain omega 0 in Rn, n bigger or equal than 2. In dimension 1, this doesn't make any sense. And you let it evolve according to the minimal curvature. Instead of taking the mean curvature, instead of taking the mean value of the principal curvature, you compute the principal curvatures and you take the minimal of those. And exactly as before, we are looking at this thing as the level set of the function of a function u of xt and see what is the equation that comes out. Okay, now as before, the gradient of u is orthogonal to the zero level set of the function. And if you assume that the norm of the gradient is equal to 1, you get that the minimal curvature is given by this expression that can be computed in terms of second derivative of u. And what is this infimum of this minimum of the principal curvatures? You take vectors, unit vectors in the tangent plane, because you have that the gradient is orthogonal to your surface. Consider the tangent plane. You take any possible vector that is tangent to your surface, to your zero level set surface, and you compute the second derivative in that direction. And among all possible directions, you are computing the minimum or the infimum, if you want. So you are taking the least possible curvature. This gives you the sectional curvature in the direction of b. This gives you the minimal curvature of your function. Okay, so what is the equation that is satisfied by these level sets? If you move the points of your surface in the direction of the normal vector to your surface according to the minimal curvature, you end up making exactly the same computations as before with this equation that says that the time derivative of u plus some operator L applied to u, and the operator L is given in this form, and it is exactly the infimum among all possible directions that are orthogonal to the gradient of u of the second derivative in that direction. Let me say one word about the equation. The equation is a parabolic equation like the previous one. This one, the mean curvature equation, is a parabolic equation. This mean curvature equation is degenerate because you don't have all the possible second derivatives of u. You have only derivative that appears in the tangential directions. And this Laplacian is not complete. You are subtracting something from the Laplacian that gives you only second derivative in the tangential thing. So it is a parabolic but degenerate elliptic parabolic equation. This equation that we found here is also parabolic. It is degenerate, but is, let me say, more degenerate than the previous one because you are only controlling one of the second derivatives in the tangential direction. So you take only the infimum. You don't have any idea about the supremum of the second derivative or any other second derivative. Okay, now we have to add something because we want to obtain the convex hull of a set K. The set K is prescribed and fixed. So you add to this equation an obstacle. What is the obstacle? You take a set K that is strictly contained into the original set. So you're saying that the set K is surrounded by your surface. So K is contained in the set where u of xt is positive. And in this set, you take another function, an auxiliary function psi that is going to be fixed independent of time, and in such a way that K is the positivity set of the function psi. So the function psi is positive inside the obstacle, inside the set K. And now you take the obstacle problem for this evolution equation. What is the obstacle problem for this evolution equation? It's the following set of equations that you can summarize according to this maximum, but let me describe it in this way. So you take as initial condition u naught. U naught is going to be positive in omega naught in your original set, and it's going to vanish. U naught is equal to 0 is your original surface at time t equals 0. Then you ask your function u of xt to be greater or equal than the obstacle at every time. So your function is going to be a strictly positive inside K for every possible time. U of xt is going to be positive inside your set K. You ask your function to be a super solution to the parabolic equation, to the parabolic evolution equation acting by minimal curvature, and it's going to be strictly a solution with equality equals to 0 when the function detaches from the obstacle. It's let me say, is far from the obstacle. And when you touch the obstacle, the only thing that you impose is one inequality. You get this bigger or equal than 0. So this is the problem written in a shorter way. You take the initial condition. This is the initial condition for a evolution equation. And you take the solution that is a solution is the maximum of these two things is equal to 0. So you have a solution to the equation, or the function is touching the obstacle psi. And since the maximum is equal to 0, both terms needs to be bigger or equal than 0 at every less or equal than 0 at every time. So the function u of xt is bigger or equal than the obstacle. And this obstacle problem, in some sense, is reproducing the thing that when you move the surface and you touch your set k, you cannot cross. So the movement of the surface is stopped when you touch your set k. Okay, the first theorem that we can prove, and that is not a surprise, is that for this obstacle problem in this setting, for these 4 equations, you have existence and uniqueness of a viscosity solution. And all these things relies on a comparison principle. The comparison principle for the minimal curvature equation, for this parabolic equation, can be proved as usual, doubling variables and making more or less the same strategy that holds or that can be done for the mean curvature equation. The only thing that you have to take into account is that this infimum is a little more degenerate than the mean curvature. So instead of a sum, you have an infimum that creates a little difficulty, but it can be done. So this first theorem that you have existence and uniqueness of a viscosity solution to your obstacle problem is not a big surprise. Okay. So one thing about the dimension 2. In dimension 2, so when you are in the plane, your surface is not a surface, it's only a curve. And for a curve in R2, you have only one curvature. So the minimal curvature is the same as the mean curvature, is the same as the maximal curvature, is the same of every curvature because you only have one curvature there. So when you are in dimension 2, the evolution problem, this evolution problem of the minimal curvature is the same as the mean curvature flow, and the mean curvature flow, also known as curve shortening flow, was studied previously by these authors, by Mercier and Misu, recently by Misu, a Japanese author, in 2023. And in fact, it was Misu's paper that turns our attention into this kind of problems. But they studied the mean curvature flow with an obstacle. And we studied the minimal curvature flow with an obstacle. But of course, in dimension 2, everything coincides. So our results are relevant or are different, strongly different from previous results in dimension bigger or equal than 3. So that's why I was telling you that my idea, or everything that you have to take in mind, is in R3, in the Euclidean domain R3, you take a surface of dimension 2. Because there you have 2 principal curvatures. One of them is the smallest one, the other is the bigger one, and the mean value of the 2 is the mean value, is the mean curvature. Okay, what happened about the asymptotic behavior of this evolution problem when the obstacle is the empty set? So when you don't have any obstacle, without any obstacle, what's happened with the minimal curvature? If you take a ball, a large ball, again, all possible curvatures of the ball are the same. So the movement by mean curvature, by the mean of the principal curvature, and the minimal one is going to be the same thing. So the ball evolves exactly as the mean curvature flow without any obstacle, and you get that the solution is also a ball, and the ball has a radius that is decreasing as satisfies an ODE and disappears in finite time again. And since you have a comparison principle for this evolution, if you take your initial surface, any initial surface that you want, and you put it inside a large ball, the large ball collapses to a point in finite time. So your surface will shrink and disappear in finite time again. So the asymptotic behavior when there is no obstacle is that everything is going to shrink and disappear. One thing that I don't know, and I will very much like to know, and I will comment on that at the end of the talk, is if you have a surface, let's say a convex surface, and you move it according to minimal curvature, if everything shrinks to a point, and if the asymptotic shape is also almost a sphere. And this I don't know, but I know for sure because of comparison that everything disappears. But when the k is different from 0, so when you have an obstacle, this is the main theorem and the main result of this talk, and you can disconnect from now on. So when the set k is different from the anti-set, and you start with something that surrounds, let me say that surrounds the convex hull of k, this condition can be very much relaxed, because what you don't want, if you take these two balls, is that the initial surface is disconnected. If it is disconnected, you will never get the tube in between. So you want something that prevents you from disconnect the two sets. Okay, this condition is a simple condition that prevents you from disconnect. So if the convex hull of the set K is contained in your initial domain, so it's contained inside your initial surface, then you obtain what you want. The movement by minimal curvature of the sets of the surfaces converges to the convex hull of your set K as t goes to infinity. These sets omega t are exactly the positivity sets of the solution of the solution to the PDE that corresponds to the level set formulation of this motion by minimal curvature. And we are not saying, bear in mind that we are not saying at any point in this talk that the zero set of this function u of xt is a smooth surface. So regularity of the zero set or regularity of the movement by minimal curvature is not present here. The only thing that we are saying, this family of set approaches the convex hull of this set K as t goes to infinity.
Just one.
Yeah, sure. Let me go back.
So I thought that the idea was that the omega t's, I mean, this you take omega 0 and you shrink it until you get to the convex hull, right? So if you don't start with I cannot imagine how you can do that if you do not have that the convex hull is contained in the original set, because otherwise how can you shrink it to the convex hull?
Okay, let me make the following picture with my hands. Assume that the original, the K is two balls, right? You may have a surface that is like this and surrounds the two balls, but is, let me say, thinner than the convex hull inside the tube that joins the two balls. If you move by minimal curvature, my claim is that if the thin thing is not too degenerate, and this is the condition that can be relaxed, then you will obtain the tube and the two balls in the limit.
Okay.
I think Willy believes that the picture in his head is that the flow is always shrinking, and in fact it isn't. Sometimes
it isn't.
Not necessarily.
Yeah, it is shrinking when the positive, when the surface is curved like this and the two mean curvatures are positive. But you may have a surface that is like this. So the curvatures are negative here, and this goes up.
Okay.
A little bit.
Just that, I mean, the picture in my head is that it's shrinking is because you use the verb shrinking at the beginning of the talk.
Sure. This is the hypersurface shrinks and disappears in finite time. It shrinks probably is not entirely correct. Is the hypersurface moves and disappears in finite time, but it collapses to something. Yeah. Yeah. Sorry about this, and thank you for the clarification as well. One thing that I don't know here, and I believe that this limit is in fact a limit. So I am not claiming that omega t is equal to the convex hull of K for some positive time. So for this evolution continues forever or not? I think that it continues forever. Okay, an idea of why this holds is the following. If you take two balls and assume that your initial surface is convex and surrounds the two balls, so this is going to shrink. And when if it happens that you reach the convex hull of these two balls, so the two balls and the cylinder inside, at this point, at the point that is on the top, for example, you have that one of the principal curvature is equal to 0, while the other is positive. So this point is not going to move anymore because the minimal curvature is equal to 0. One of the two is equal to 0, the other one is positive, so this point is not moving anymore. So any point when you touch, if it happens that you touch the convex hull, you are not going to enter into the convex hull, you are not going to move anymore. And the convex hull of the two balls, in fact, is a stationary solution to this geometric evolution. And this does not happen if you use the usual mean curvature flow, because if you start with the same configuration with the two balls and you surround them with a surface and you reach a point where you touch the convex hull of these two balls, at this point, one of the two curvatures is strictly positive, while the other is 0. So this point is moving inwards. And what you get in the two balls is that the tube starts to shrink a little bit, and this is not convex anymore. One question that should be interesting to answer as well is that if you start with a convex initial configuration with omega 0 being the boundary of a convex set, if the evolution remains convex forever, the evolution by minimal curvature. And I think that this is true, but this is not proved, and this is not the reason why this convergence holds. Okay, now let me go to a commercial break, let me say. And the commercial break, you can relax a little bit, take a slurp of coffee, and I will say something about the journal, about Orbita Mathematica. Okay, Orbita Mathematica, as was already said, is the journal of the Umalca Union. This is the mathematical union for Latin America and the Caribbean. So you can imagine that there are a lot of countries inside this Umalca union. And okay, the main editors, the managing editors are listed there. I will not list the full set of editors, but I encourage you to look at this address that I pointed there. So if you Google Orbita Mathematica, you will find it very, very easily. And of course, this is a journal, and since this is the Orbita Mathematica seminar, I imagine that I have to say something about the journal. The journal, let me say that I expect the journal to be a very good journal. Okay, now let me say something about the proof of the main result. So this was the main result. When you move your surface according to the minimal curvature flow instead of the mean curvature flow with an obstacle, with these two K as an obstacle, you obtain the convex hull of this K. And you obtain this looking at the positivity sets of an auxiliary function u of xt, taking the level set formulation of the problem with an obstacle, and the K, what is the obstacle K? The K is encoded in this function psi that happens to be positive inside K. So now let me say something about the proof of this thing. And the proof is not a PDE proof. It's not. It relies on some game theoretical approximation of this parabolic problem, of the parabolic PDE. And for me, this is very nice, and I like it very much because game theory comes into play and gives you a proof concerning some partial differential equation, or the solution to a partial differential equations that up to now I cannot prove by poor PDE methods. So this is a proof using a different technique, let me say, a different idea. So this game is a two-person zero-sum game. So two people try to play one against the other. We name the two players Paul and Carol, just because those names were used before in the literature. So Paul and Carol. One way of naming this that I like it more, but Paul and Carol is okay, is to call Paul Max and Carol Mini, because Paul wants to maximize something and Carol wants to minimize something. So, but let us stuck with Paul and Carol. Okay, the first thing is that you take some small epsilon and you enlarge a little bit your set K. And why you enlarge a little bit your set K? Because you don't want to miss K doing discrete things. So you enlarge a little bit, adding a ball of exactly this radius. And again, capital N is the dimension of the space. So you take two functions, the function omega naught, and your initial surface is the boundary of this set omega 0. And you take a function psi epsilon. This will depend on the parameter epsilon as well, because you want this to be positive inside your set K epsilon that was the original set K, enlarged a little bit. Take a point that is the initial position of the game and some initial time that is positive. And now you were going to move the game according to these rules. The movements are going to be discrete. At every round of the game, at every movement of the game, Paul, the first player, chooses a vector, chooses a direction, any direction that he wants. And Carol, the second player, chooses a sign, that is, chooses plus or minus 1. And the next position of the game is the previous position, plus or minus, and this plus or minus depends on Carol's choice, times the direction that is Paul choices, times the step size that is epsilon. So Paul chooses a vector. Now Carol chooses to go in this direction or in the opposite one. So she can choose to reverse the direction that Paul chooses. And now you make a step forward or a step backward according to the choices of psi epsilon. And at the same time, you decrease t by epsilon squared. This 1/2 is just for a normalization constant, just for the equation to be, instead of 1/2 the time derivative, the time derivative. So you decrease time by epsilon squared, and you move in a space in X according to the two choices of Paul and Carol. The first player, Paul, chooses a vector. The second player, Carol, chooses a sign for the vector. And now you get another position. You continue playing, and when time ends, so after this amount, the integral part of 2 times x naught over epsilon squared, so when you decrease in time and when time expires, when you reach time t equals to 0 or negative, then you stop the game, and the terminal cost of the terminal payoff is given by the function u naught. So you get that Paul wins this amount of money and Carol has to pay this amount of money. If u naught is positive, Paul is getting money, and if u naught is negative, it's Carol who is getting money because the payment for Paul is negative. To these rules, you add another stopping rule that says that at any movement of the game, at any point, Paul may decide to stop the game, I quit the game, and if he decides to do that, then Carol pays the amount given by the obstacle function, by this psi epsilon of the position. Okay, this game has a value function. What is the value function? The two players now have to choose strategies. What is a strategy for Paul? A strategy for Paul is the choice that he will make of the vector of the direction of norm 1 at every possible point, at any possible position, at any possible time. And what is a strategy for Carol is the possible choices that Carol has to choose the sign plus or minus 1 provided that Paul chooses the vector vi. So she has to decide which sign is going to use at every possible point, at any possible time, at any possible vector v. Once you fix the two strategies, the poor Paul is going to try to maximize. So it's going to try to take the supremum of the final payoff according to all possible strategies, and Carol is trying to minimize. She will try to minimize the final payoff. So this is the value of the game, and the value of the game is well defined and verifies a PDE. It's not a PDE because you don't have derivative, but it's a sort of discretization of the previous PDE. So this is a discrete setting for the PDE. And what does it say? It says what you expect of the value of the game. The value of the game is the same as the value of the game, provided that you play one round. If you play one round, the player who can stop is Paul, and he's maximizing the expected payoff. So this is the maximum between two things, between the obstacle. If Paul decides to stop, then your epsilon, the value of the game, is equal to the obstacle function. And if he decides to play, you get this thing. So you take the supremum among all possible directions. This is Paul choices. The minimum among all possible signs, plus or minus 1. This is Carol choices. And the expected value, provided that you make one play, and provided that you make one play, is that you decrease time by epsilon square, and you move according to this thing that it was the sign chosen by Carol and the vector chosen by Paul. And of course, this equation holds when t is positive. When t is negative or equal to 0, then you get the initial condition. What the players want to do? Okay, Paul wants to stay inside omega 0. Why he wants to stay inside omega 0? Because omega 0 was the set where u0 is positive. Omega 0 is where u0 is positive. So if you reach omega 0 for t equals to 0, then Paul is winning, is getting some money. So Paul wants to stay inside your omega 0 set, and also wants to reach the obstacle, because when the position of the game reaches the obstacle, he can stop and he will connect money, because the obstacle function, this psi epsilon, is positive in this set k epsilon. Okay, but what does Carol wants to do? Carol will try to escape outside omega 0. So we want to go outside omega 0, but she has to do this in a clever way, evading always, all the time. She wants to not reach this k epsilon. So Carol wants to go outside omega 0, outside the region, without touching the obstacle at every movement. If there is no obstacle, one can show that Carol has a strategy, may choose the sign in such a way that you exit any possible ball if you play a lot of times. So without obstacle, this game is clearly favorable to Carol. It is the obstacle that prevents Carol from winning for every possible time, or for large times, let me say. So Paul has to take advantage of the obstacle. And of course, you can imagine, you can draw pictures in a blackboard, and we do so, and we laugh a lot, trying to see what is the optimal strategy for one of the players, how one of the players may choose one vector or another vector in order to stay inside omega naught, or instead take the two obstacles. If you take the two balls and you start somewhere in between, so you start in the convex hull of the two balls, then Paul may choose a vector in this direction. So may choose a vector in the direction of the two balls, and Carol will never be able to exit this line, because whatever sign she chooses, you will stay always inside there, and you cannot jump over the set k and run. And this reason that you cannot jump over the set K and run with the steps of psi epsilon is exactly the reason that forces us says that we have to enlarge a little bit the set K, because the set K can be very small compared with epsilon in such a way that with one movement you can jump over the set K. With this, adding this ball, it is not possible to do that. And that's the reason for enlarging a little bit the set K. Okay, what does happens with this movement is that you can introduce, as before, the positivity sets of the value functions of the game, this omega t epsilon that are the positivity things. And what are these sets? These sets at time t are the sets where Paul will win something, will get some positive payoff playing this game started at x at this set at time t. And of course, Carol is going to lose the same amount of money because this is a zero-sum game. And the key point here is that the K epsilon, the set where the obstacle is positive, with this obstacle function psi epsilon is positive, is always contained in the set omega t, because Paul may decide to stop at any possible time. So when you have a point in this set, you are sure that the optimal strategy for Paul gives at least psi epsilon. So what you get is something that is strictly positive for all possible times. So this line says that you will never miss the obstacle K epsilon considering the sets omega epsilon t. And now you want to compute two limits. This omega epsilon t, you want to compute the limit as epsilon goes to 0 and the limit as t goes to infinity. First, we can compute the limit as epsilon goes to 0 for the value functions. And the value functions of this game, the theorem says that the value functions of this game converge locally uniformly as epsilon goes to 0, as the size of the step goes to 0 to u, and u is the unique solution to the obstacle problem, to the Volcker PDE. So the partial differential equation that encodes the flow by minimal curvature with an obstacle can be approximated using solution to this game. And for this game, you can analyze, let me say, which are optimal strategies or quasi-optimal strategies. You can play with the strategies of the game, trying to get some information about u epsilon. So you take these sets, those are the positivity sets and the positivity set of the limit, and from uniform conversions, you get that the limit that you want, this omega t, is quite close, so it's comparable with the limit as epsilon goes to 0 of the positivity set of the value function of the game. And okay, you have a lim sup and a lim inf and a closure there, but it's almost the same. So it's not only that the functions approximate the function, it is also that the positivity sets approximates the positivity sets. And concerning the limit as t goes to infinity, because you want both limit in this set, you want the limit as t goes to 0, as t goes to infinity, and as epsilon goes to 0. As epsilon goes to 0 is this result. As epsilon goes to 0, you get conversions of the functions and conversions of the sets. As t goes to infinity, what you get is this line over there, and this is the result that gives you the asymptotic behavior of the sets omega t of our original problem, that says that if you take this assumption, that can be a little relaxed, as I mentioned before, it holds that the convex set, the convex hull of K, is contained in the lim inf as t goes to infinity of this set omega epsilon, is contained in the lim sup, this inclusion is trivial, is contained in the convex hull of K epsilon. K epsilon was the larger domain, the largest set K, and this is also contained in the convex hull of K plus a small ball. So you see that the two extremes of this chain of inclusions are quite close when epsilon goes to 0. So now you take the limit as epsilon goes to 0 in all these things, and what you get is the original theorem, the main result that says that the convex hull of the set K is the limit as t goes to infinity of these sets omega t. And the strategy for that is prove that these sets omega epsilon t are close to the set omega t, and the limit as t goes to infinity of these sets omega epsilon t is, let me say, almost the convex hull of K time, with an error that depends on epsilon. Okay, things to be done, or things that I don't know how to do and I will very much like to do or to see them done. Let me say, the first is to find a pure PDE proof of the conversions without the game, not using the game. And you can tell me, okay, why are not you don't like the game? No, I like the game very much. And of course, I like to play games. But I would like to see a pure PDE proof, and something that I try to prove without success is if you take a convex surface that surrounds the obstacle, prove that the movement by minimal curvature of this convex surface remain convex for every time, and that the distance from the convex hull of the set K to the surface is decreasing, and in fact strictly decreasing with time. And this I don't know. I don't know this using the PDE. I don't know how to prove it using only the PDE problem. Now, the second point is try to study another evolution that I like it also very much, and I am sure that this works as well, but I don't know how, is to move a point. Instead of moving the point according to the minimal curvature, try to take the product of the curvatures. And this is called the Gaussian curvature of the surface. If you do that, I believe that you will obtain the same thing, because if you remember the picture, this picture, at points like this in the tube, you have that one of the curvature is equal to 0, one of the principal curvature is equal to 0, while the other curvature is positive, so the product of the two is also 0. So your movement will also stop when you touch this cylinder. So this movement by the product of the two curvatures, I believe that it will also work. Okay, also with an obstacle to recover the same thing, to recover the let me say, the convex hull of the obstacle. And why I will try to do this? Because my claim here is that the flow by minimal curvature is not the only possibility. If you want to recover the convex hull of an obstacle, maybe there are other geometric movement that gives you the same. This one will give you the same asymptotic behavior. And on top of that, one of the two is going to be faster than the other. And I believe that this one, the product of the two curvatures, is going to be faster than the other. But I am not completely sure, of course. Because if I was completely sure, this is not in the section to be done. Okay, for the next thing is that for the obstacle, without any obstacle, the surface shrinks, and you want to prove that when you shrink the surface by minimal curvature, assume that the initial surface is convex, it remains convex and shrinks to a point. And when it shrinks to a point, it's going to be nearly spherical. But the key point here is that for minimal curvature, you want to prove this, but for maximal curvature, this is not going to happen in general, because you can build examples, for example, a tube with two small half balls at the end of the tubes. This is going to be self-similar, and it's going to collapse not to a point, but to a segment. And for the flow by maximal curvature, I think that we can build examples of surfaces that collapses in curves, not only in segments on points. And the fourth point is something that I will very much like to enter into this, is that discrete versions of this thing. So you are moving a surface and you want to obtain something continuous, but assume that you have a lot of points that are distributed according to some distribution. So you have some distribution on a finite, on a, say, a compact set in this screen, and you take some random points inside, a lot of random points inside. Some of them are red. Let me say that the points that fit into these two balls are marked red, and the other ones are black. And you want to remove the black ones that are not in the convex hull of the red ones. So you want at the end to get only the red ones and remove all the others, and remove all the others in such a way that you see the layers. So you have an exterior layer, then you have another one, then you have another one. You're peeling your orange in such a way that you recover the convex hull at the end, but you have to make it all this discrete. We have an algorithm, a sort of algorithm to do this, and it corresponds more or less to this equation, to the product of the two curvatures, or the product to the two curvatures to the 1/2. But we have to refine this thing and to think better how to do it. Okay, so thank you very much, and thank you for the invitation again, and thank you for your attention.
Yes. Well,
All right. I see people clapping. Is there any question?
Is there any
No,
questions? Yeah.
Is there any question?
No.
I know, I mean, I asked too many questions, but what is, I mean, there must be some built-in thing in the way you set up the problem that guarantees that in the limit, what you get is convex. Right? So where does this show up? I mean, what guarantees that the limit of these sets gives you a convex set?
let me add, where are you using that K is convex?
No. K is not convex. K in the example, in the model example,
sorry,
is the
you
union
want to
of two
find the
balls.
convex hull? No, sorry.
No,
I haven't.
The omega zero is not assumed to be convex even.
Yeah, okay.
no. Omega zero is not assumed to be convex either.
Yeah.
And the two balls are not convex. You want to find the two balls and the tube as the limit of the evolution of this surface.
Mm-hmm.
Let me do it with my hands. Let me say, if you take a surface and the surface is curved like this, you want to move inside, because the two curvatures are positive, the minimal curvature is positive, you are moving in this direction. If the surface is curved like this now, one of the two curvatures is negative, so you're moving outside because you reverse the sign. So negative curvature will go up, and you will try to make this convex. And when you are convex, so everything is rounded with positive curvature in every possible direction, you go inside, you shrink. This is the movement that you are making. But it is not proved anywhere, and we are not proving this in the paper, that when you start with a convex set, you remain convex forever. And the proof that in the limit you get this tube is based on this one. Is based on the game. And for the game, when you are inside the convex hull of these two balls, you have a clear strategy. Paul has a clear strategy, not me, but Paul has a clear strategy that is point in this direction. If you point in this direction, you will never exit this direction. You will remain there forever. And when time is exhausted, you will get something positive because you are assuming that the convex hull is contained in omega zero. So for this case, you will be happy forever. And outside the convex hull, Carol, the other player, she has a strategy that kicks you out of every possible ball. And being outside the convex hull, this you have to prove it, the strategy of Carol never touches the obstacle. So Carol may have a way of choosing the signs in such a way that you exit every possible ball without touching the two balls if you're outside the convex hull of the set. And this is the proof of this result. Okay, this answer more or less your question, because this is the intuition. This is the intuition that I have behind this movement of minimal curvature.
I see.
Other questions? Hector.
Hola, Julio. Thank you for your talk. Very nice. So
Thank you very much.
I imagine that the surface sticks to the obstacle in a tangential fashion. Did you prove this? And do you have the picture of what would be the blow-ups at these separation branching points? Or is not true what I'm saying?
No. I will not say that it is true or will not true. I don't have any idea. And we are not proving regularity results for the obstacle problem, for this obstacle problem. So
and do you expect it to be tangential or something else?
I expect it to be tangential, yeah. As the usual obstacle problem, I expect that the solution detaches from the obstacle in a tangential way. Let me say that I also expect that solutions to this equation, if U naught and psi are smooth enough, and what that means is smooth enough, but are smooth enough, then the solution is C1 alpha. But I will not expect more regularity than that, because for the convex envelope of a boundary data, the optimal regularity, I think that is C1 alpha, or if it's not going to be C2 at least.
I think it's C11.
And this is C11, and this is your result. This is Silvestre.
No. The
Oberman,
convex envelope
Silvestre.
is no. The convex. I have a paper with for the Dirichlet problem. The convex envelope is exactly, like literally, in a paper by De Filippis and Figali, which is much more recent than you would expect. Meaning that given a smooth obstacle, the convex envelope is a C11 function. It's a C11 surface.
Yeah, for the minimal curvature.
Let me
say that
for the minimal curvature, the obstacle problem is C11, and that's literally a result of Figali and De Filippis from not too long ago.
Okay.
But what you're doing here is the parabolic problem, and so it's interesting the question by Hector of what kind of regularity can you expect before the asymptotic limit, like for throughout the process for the parabolic problem.
Yeah.
All right. Anything else? Okay. All right. So I guess this is all. Thank you for everybody for coming, and thank you, Julio, for giving the talk.
Okay. Thank you very much.
Recording stopped.